Welcome to Understand the Math. In this video, we're going to explore how exponential growth and decay apply to real-world problems. We'll look at both discrete and continuous models and walk through 5 fully worked out examples. By the end of this video, you'll know how to use the right formula and solve these types of problems with confidence. We're going to start with discrete models. These are situations where the change happens at specific intervals, like every year, every hour, or every 30 minutes. For these types of problems, we're going to use the formula A is equal to P times 1 plus or minus R raised to the T power. P is just the initial amount, A is the final amount, R is our growth or decay rate per time period, and then T is just the number of time periods. We're going to walk through 3 examples where we use this formula, and then we'll go over the formula for continuous models. The first example that we're going to look at is about population growth. We're told that a town's population is currently 50,000 and is increasing by 2.5% per year. We're asked to find out what will the population be in 10 years. Because the population is increasing at a set percentage rate per year, we're going to use the formula for discrete growth. That formula is A is equal to P times 1 plus R. We're using the plus because it's increasing, all raised to the T power. Let's now write down what P, R, and T are equal to. Our P is our initial amount, and that is 50,000 people. You always want to remember to write down the units. R is our growth rate per time period, and that's equal to 2.5%. And then T is our number of time periods. Because our growth rate is a percent per year, our time periods are going to be in terms of years, and we want to find the population in 10 years, so T is going to be equal to 10 years. Before we substitute these values into our formula, we need to convert R to a decimal. Whenever you have a percent, that's just the number divided by 100. So what you're going to do is move the decimal 2 places to the left, and we get 0.025. Now we can take these values and substitute them into our formula. We have A is equal to P, which is 50,000, times 1 plus R, which we just calculated to be 0.025, raised to the T, which is 10. What you want to do now is take this expression and put it into your calculator. And when you do that, you're going to get the number 64,004.23 people. I think it's a really good habit to get into when you write the answer for a word problem to write your answer in a sentence and make sure that your sentence answers what you're being asked to find. We were being asked, what will the population be in 10 years? So our answer is going to be the population will be approximately 64,004 in 10 years. We had to use the word approximately because we had to round our final answer down because our answer had to be in terms of a whole person. Let's now look at our next example. Our second example is about medication in the bloodstream. A 200 milligram dose of a medication loses 15% of its concentration each hour. How much medication remains after 5 hours? We have a percentage loss in this problem per hour. That means that we are again going to use our discrete model and it's A is equal to P times 1 minus R to the T. I used a minus sign this time because a loss indicates decay. Let's now write down what P, R, and T are equal to. Our P is our initial amount, and it is 200 milligrams. We need to make sure and put the units down. R is our decay rate, and that is 15%. Let's go ahead and change that to a decimal. We're going to take 15 and divide it by 100, and we get 0.15. Just moving the decimal 2 spaces to the left. And then lastly, T is our time, and it is 5 hours. Notice that our percentage loss is per hour. These units need to match up, so we can say that T is just 5 hours. Now let's go ahead and put all of this into our formula. We have A is equal to 200 times 1 minus 0.15 raised to the 5 power. When we put that into our calculator, we get 88.74, and let's include units. It is going to be milligrams. Notice that the units for A match up with the units for P. Now we need to write our answer in a sentence. We are asked to find how much medication remains after 5 hours. So we can say that 88.74 milligrams remains after 5 hours. Let's now look at our third example. This is our hardest discrete example. We're going to be looking at a problem on radioactive decay with half-life. Our problem states that a radioactive substance begins with 640 grams. It has a half-life of 30 minutes. That just means that in 30 minutes, half of the substance will have decayed. We're asked to find how much of the substance will remain after 3 hours. In this problem, we're told that the decay happens every 30 minutes. So we are going to use the discrete model. A is equal to P. And now we need to decide if we have a positive in front of the R or a negative. Because we're talking about decay, we have a negative. So we're going to write down 1 minus R to the T. Our P is the amount that we start with, which is 640 grams. R is the decay rate, and we are not told that. So let's just put a little question mark here. And in parentheses, I'm going to write that the half-life is equal to 30 minutes. Because we're going to use that to find the decay rate. And then T is the number of 30-minute time periods in 3 hours. And we're going to have to calculate that. Let's begin by finding R. So I'm going to write down, we're going to find R. We're going to use half-life to find R. We're told that we have a half-life of 30 minutes. So that means in one 30-minute time period, the amount that we're going to have is half of what we started. So we're going to say 1/2 P, we're plugging that in for A, is equal to P times 1 minus R to the 1. So in one time period, we're going to have half of the substance remaining. Notice that our P's can cancel, and we're just left with 1 minus R is equal to 1/2. We don't even need to solve for R because we're going to be plugging 1 minus R back up into our formula. Now what we're going to do is find our time T. We already talked about T being the number of 30-minute time periods in 3 hours. So let's write down that T is going to be 3 hours. And then we're going to convert that to minutes. So this is 60 minutes per hour. And each time period is 30 minutes. So we're going to divide this by 30 minutes. So this becomes 180 divided by 30, which is 6. That answer makes sense because we know that there are 2 30-minute time periods in 1 hour, so that makes sense that there are 6 30-minute time periods in 3 hours. Another way that we could have thought about this is we could have used the formula that T is the total time divided by the half-life. So that is just 180 divided by 30, which is 6. Now what we're going to do is find A. So we're going to substitute back in 1 minus R and T as well as P. And we get that A is equal to 640 times 1 minus R, which we found to be 1/2, raised to the T, which is 6. Now all you have to do is plug these values into your calculator. And it turns out that our answer is equal to 10 grams. Let's now look back up at our problem so that we can write our answer. We wanted to find how much of the substance will remain after 3 hours. So we can write down that 10 grams will remain after 10 hours. Before we go on, I want to write down an alternate formula that we could have used because this is what we call a discrete half-life problem. The formula is A is equal to P times 1/2 to the T divided by H. The T in this formula is different than the T that we used. The T in this formula is the total time. So in our problem, that would have been 180 minutes. And then H is the half-life. This gives the same answer as the formula that we used, but it's easier because you don't have to calculate 1 minus R. I want to clarify one more thing about this problem. It's important to remember that in the real world, radioactive decay doesn't happen in sudden distinct jumps exactly when a half-life period ends. Instead, radioactive decay is a constant, smooth, continuous process where atoms are decaying every single moment. When we look at problem number 5 in a few minutes, we're going to use the continuous formula for half-life that scientists use to represent this type of change accurately. We're going to now look at 2 example problems that involve continuous growth or decay. In our first example, we are going to look at bacterial growth. We're told that a bacterial culture starts with 100 cells and grows continuously at a rate of 20% per hour. We're asked to determine how many cells will there be after 12 hours. This problem told us that the cells were going to grow continuously. Because of that, we have to use what's called the continuous growth model. Let's go back to page 1 where I have that equation listed and let's look at it. Let's look at the formula for continuous growth or decay. The formula is A is equal to P times E raised to the KT power. Just like in the discrete model, P is the initial amount and A is the final amount. K is called the continuous growth or decay rate, and then T is the amount of time that's passed. Let's now go back to page 3 and go ahead and complete that example. Let's begin by writing down the formula that we're going to use. It's A is equal to P E to the KT. P is our beginning amount, which is 100 cells. K is our continuous growth or decay rate, and it's equal to 20%. Let's go ahead and let's convert that. We're going to take 20, we're going to divide it by 100, which gives us 0.2. Just moving the decimal point 2 places to the left. And then T is the amount of time that has passed, and that's equal to 12 hours. Notice that this unit matches up with this unit. So let's write down T is equal to 12 hours. Now all we have to do is take these values and substitute them back into our formula. So we have A is equal to P, which is 100, times E to the K, which is 0.2, times T, which is 12. E is Euler's constant, and it is approximately 2.71828. You can use that in case you don't have a calculator that has E in it. You're going to put all these values into your calculator, and we end up with an answer of 1102.32 cells. Notice that the units that we get for our answer are the same as the units for our initial amount. Since we can't have a partial cell, when we write down our answer, we are going to have to round this number down to 1,102. Let's go ahead and write our answer. Our answer is going to be, there will be 1,102 cells after 12 hours. Let's now look at our next example. This is another radioactive decay example with half-life, except in this problem, we have continuous decay. We're told that we have a radioactive substance that has a half-life of 7 years. If you start with 500 grams, how much remains after 20 years? When we have a problem like this that has a half-life of 7 years, we have to assume that we are talking about continuous decay. So we can write down the formula A is equal to P E to the KT. Let's now find out what our variables are. P is the amount that we start with, which is 500 grams. K is our continuous growth or decay rate, and that we're actually not given, but it is related to the half-life. So let's write down that we have a half-life equal to 7 years. So we'll actually have to find K. T is the amount of time has passed, and that is 20 years. We're going to begin by finding K. And honestly, that's the hardest part of this problem. We are going to use half-life to find K. The half-life equaling 7 years tells us that in 7 years, there is going to be 1/2 of the substance remaining. So we can write down that our amount A is going to be 1/2 what we start with is equal to P, which is what we start with, E to the K, and then T is going to be 7 years, so we're going to substitute T is equal to 7. Our P's cancel, so we have 1/2 is equal to E to the 7K. We need to find K, and because K is up in the exponent, we have to take the natural log of both sides to get K out of the exponent. This gives us natural log 1/2 on the left is equal to natural log E to the 7K on the right. The power rule for logs tells us that we can take that 7K out in front, and we're just left with ln of E. And then we know that natural log of E is equal to 1, so this is just 7K. Hang with me, we almost have K. All we have to do now is divide by 7 because we have natural log 1/2 is equal to 7k. So we can say that k is 1/7 times natural log 1/2. Now we can go ahead and substitute k and p and t into our original formula. We have that a is going to be p, which is 500, times e to the k, which is 1/7 ln 1/2, times t, which is 20 years. I'm going to rearrange things up in our exponent, and I'm going to write this as 500 times e to the ln 1/2 times 20 divided by 7. When we simplify this, this just becomes 500 times 1/2 raised to the 20 divided by 7. You actually don't have to do all that simplification, and you could have just put this expression into your calculator. But I just wanted to show you how it simplifies. When you put 500 times 1/2 raised to the 20 divided by 7 into a calculator, you get 69.01 grams. So we can write that 69.01 grams remain after 20 years. Before we finish, I want to point out something really important. An alternate formula that you could use for continuous half-life problems is A is equal to P times 1/2 to the T divided by H, where T is the same T that we just used, the amount of time that's passed, and then H is the half-life. Both formulas will give you the same answer, but this formula is easier to use because you don't have to find K. And that's it. We covered a lot. Here's just a few things to keep in mind. You want to use the discrete model when changes happen at fixed intervals, and you want to use the continuous model when change is happening all the time. Always be careful to convert your percentages to decimals and pay attention to the units of time.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.